Hi everybody, welcome back. In your previous lesson, you should have looked at what are known as Lewis dot structures. Basically, that's like a schematic diagram for a molecule. It shows you how the valence electrons help to hold together the atoms of a molecule. Okay. Now, in this lesson, we're going to take Lewis dot structure and use it to determine the actual shape of the molecule. And what you need to keep in mind is that molecules are three-dimensional objects. They're extremely small, but they are still 3D objects, just like a pen or a phone or, a little pad of paper, whatever the case may be. Just like these are 3D objects, molecules are also three-dimensional things. So to determine the shape of a molecule, we use what's known as VSEPR theory, or the VSEPR model. To break it down, valence shell, electron pair, repulsion model. Okay. Now don't let all those terms intimidate you. If we break it down here, we're talking about pairs of electrons that are valence electrons that repel each other. That's the idea. And if you read the theory here, that's what we're talking about. Pairs of electrons, whether they're in a bond or not, repel one another because they have a negative charge, and like charges repel. Okay? Now what happens in a molecule, imagine we have oxygen here with hydrogens attached to it, and then these electrons, known as lone pairs, meaning they are not bound to another atom, they are only part of the oxygen. These electrons will arrange themselves in a way to minimize the repulsion between them, okay? And that is going to cause the molecule to have a particular shape, okay? So that's the idea behind this theory. Atoms and electrons arrange themselves to minimize repulsion between electrons, and in so doing, the molecule gets a shape, okay? Quick pause here. So, how do you actually do VSEPR theory? How does this work? So, you follow these steps. Step 1, you do a Lewis dot structure, like you did yesterday in the previous lesson. Okay? Now, you can use VSEPR theory for large or small molecules. When you look at any molecular shape, the basis behind knowing that shape is this theory. Okay? Now, because you're just learning about this, we're going to deal with simple molecules with simple shape, with not many atoms. Okay? So your first step then is to do a Lewis dot structure, do your electron dot structure. Then you're going to determine a central atom, call it A. Okay? Typically, if carbon's present, it's carbon, or when you're looking at the formula, you can put the first element first, or the one with the least electronegativity. Typically, will go in the middle, okay? So you determine your central atom, and you deem it A. And then you do these next two things. You look at the central atom, and you count up how many other atoms are connected to it. Call those X, okay? Why? That's just the agreed upon way of doing this. Also, you look for lone pairs. These are pairs of electrons not connected to another atom. And we'll call those E, okay? So if you look at the water down below here, it has two X's, two other atoms, this H in this one, attached to the oxygen. So X would be 2. There are also two lone pairs, these and these. So X would also be 2, okay? So that's your next step. Determine the X and E, other atoms and lone pairs connected to that central atom, okay? And then you use that to determine an Ax formula, where the number of X and E become little subscripts for X and E, okay? What do you do with that? You compare it against a chart to determine the shape. And the chart I will show you in just a moment. Okay? So in a nutshell, that's how you use this theory to determine the shape around a central atom. Okay? Couple things here, okay? Remember that there are some exceptions to the octet rule, okay? Boron and beryllium can have less than 8 valence electrons. They're stable with less than 8, okay? More than 2, but less than 8. That will influence their shape. The other two, the xenon and the sulfur, some elements can actually have more than 8 valence electrons if they're part of a bond, part of a compound. What you do in that case, anything extra you put on the central atom. So if you have extra atoms or extra valence electrons, you just stick those on the central atom, okay? And some of our VSEPR shapes take into account the fact that that happens, okay? For polyatomic ions, whatever the charge is, if it's a negative charge, you add that many valence electrons, and if it's a positive charge, you take away that many electrons when you do a Lewis dot structure, okay? And that will also affect the shape that you determine through the VSEPR theory, okay? So these exceptions and polyatomic ions, you want to keep those in mind as you're doing this, okay? Now, let's look at some examples. We have 6. Oh, I'm sorry. Before we do that, though, here's the VSEPR chart. Forgive me. Give me just a moment here. Anyway, there's the chart, okay? So again, when you determine that AXE formula, literally all you have to do then is compare it against this chart and look for the proper shape, okay? And it will tell you the shape, where A is the central atom, the X's are the atoms connected to the central atom, and the little dots in blue that you see there, those are lone pairs, okay? Now the shape refers to the atoms, not to the lone pairs. So for instance, if you look at the third, if you look at AX2E1, which is a bent shape, that bent shape only refers to the atoms in the molecule, not to the lone pairs on the central atom, okay? So once you know your X formula, you compare it to the chart, and that tells you the shape of the molecule, okay? Okay, let's take a look at our 6 examples. The first one is BeH2 beryllium hydride, okay? The Lewis dot structure is completed, and you see it there to the right, okay? Take a moment and determine the X formula. Okay, so when you look at Be, the central atom, how many atoms are connected to it? 2. Lone pairs? There are none. So our X formula, AX2, is the X formula. So again, compare that to the chart and determine the shape, okay? When you do that, the shape is linear, okay? So imagine a straight line, like this pen. Beryllium would be in the middle, and the hydrogens would be on either side. And the 3 atoms are arranged in a line. The shape of this molecule is linear, okay? Bond angles, you might remember a straight line has an angle of 180 degrees, okay? Now, in terms of polarity, this molecule is nonpolar, okay? And the way you determine that, you look at electronegativity. You would also look at the shape of the molecule. We'll get into that in our next lesson, okay? You'll learn how to parse all that out. Okay. Awkward pause. Okay, let's look at another one. So we have CH4, also known as methane, and there's the Lewis dot structure in the upper right-hand corner there, okay? Carbon surrounded by hydrogens. So take a moment and see if you can determine first the X formula. Okay. How many atoms are connected? Oh, by the way, carbon is the center atom here. Okay. How many atoms are connected to it? 4. 1, 2, 3, 4. Now, lone pairs, there are none. Okay, because all these dots are connected to carbon and one of the other hydrogens. So you can see here, no lone pairs. Okay, so what is the X formula? AX4. Carbon is A, the hydrogens are the X's, there are 4, and no lone pairs, AX4. Okay, so take a moment then and see if you can determine the shape of methane. Okay, if you said this tetrahedral, you're correct. Think of it as a tripod with one leg sticking up out of the center. As you can see here, there's a sketch. Carbon with 3 H's sticking out at equal angles to each other, and then one hydrogen sticking up out from the carbon. And the angles there are all 109 degrees. Polarity, it's nonpolar. Okay. So that's your second example, methane, which is natural, a form of natural gas. We burn it for energy. The shape of a methane molecule is tetrahedral. Okay. All right, let's look at 4 more. Again, the idea here, what shape does the molecule have? Here's boron trifluoride, BF3, and you can see the Lewis dot structure. This is one where boron is satisfied with less than an octet. Okay? So take a moment. What is the X formula? Okay. Atoms on center, 3. Lone pairs on center, none. 3 atoms and no lone pairs. So X formula, AX3. Okay. What's the shape then? Take a moment and see if you can determine that. If you said trigonal planar, you are correct. Okay. Think of the shape as a flat triangle. Okay. Like maybe a kite or a tortilla chip, maybe a Dorito or something. Yes, Doritos. Sorry. Yeah, in moderation, right? There you go. But yeah, think of it as like a flat chip, a flat triangle, something like that. The angles here, 120 degrees. Polarity, it's nonpolar. Okay, so that's boron trifluoride. Has a flat triangular shape. And again, the shape refers to the atoms in the molecule, the boron, and those 3 fluorines. Okay? All right, 3 more. Let's take a look. Next one, sulfur, nitrogen, fluorine there. Okay. There's only a dot structure, upper right again. Take a moment. What's the X formula? Okay, there are 2 atoms on center. That's right, sulfur, fluorine, nitrogen, we put in the middle. Lone pairs, there it is, 1 lone pair. Notice those dots are on the central atom. They are not part of another bond. Okay, so our X formula, AX2E1. Okay, take a moment and see if you can determine the shape of the molecule. Did you say bent? Very good. It's a bent shape. That's right. Again, referring to the atoms here, fluorine to nitrogen to sulfur is a bent or angular shape, like a boomerang. 120-degree angle. This is a polar molecule. Okay? Apologies. Come on now. Good. All right, 2 more. Next one, phosphorus trichloride. And there's your Lewis dot structure in the upper right again. Take a moment, see if you can determine the X formula. What is it? Not to be confused with body spray. It's a formula, not a spray. Sorry, like axe. Yeah, it's a bad joke. My apologies. Okay. 3 atoms on center. Phosphorus is in the middle. Chlorines, we have 3 connected to it. These 2 dots right here, that's right, that's a lone pair. Okay? So the Axe formula, AX3E1. Take a moment and determine the shape. Okay, what is it? Trigonal pyramidal. It's a 3-sided pyramid in 3 dimensions. Okay, imagine the chlorines at the base of the pyramid, with the phosphorus being like the apex, the top of the pyramid. That's the shape. Okay, bond angles here, 109 degrees. Polarity, this one ends up being polar. And again, we'll get into those ins and outs next week. Okay, but this molecule would be polar. Okay. All right, one more here. Okay, everybody. So one more here. Maybe. There we go. Okay, so the last one is water, H2O, and there's a Lewis dot structure. Okay. Take a moment, see if you can figure out the Axe formula. Okay, there are 2 atoms on center, H and H, and there are 2 lone pairs, here and here. So the Axe formula, AX2E2. Okay? Take a moment then and see if you can determine the shape of the molecule. The shape is a bent shape. And again, the shape refers to the atoms, the H, O, and H. The angle, 109 degrees. Okay? So water shape is a bent shape. Polarity, water is polar. And like I said, we'll get into that piece a bit in the next lesson. Okay? So the idea here, folks, with all these details, we're simply determining the shape of a molecule in 3 dimensions. What is its shape? All right, thanks, everybody. I'll see you next time. All right.